In today's video, we'll look at logarithmic differentiation used as a tool to solve complicated derivatives that might have products, quotients, powers that are quite difficult. Now, when we say we're going to use this method of logarithmic differentiation, we are actually talking that we're going to use a natural log. The reason being, the derivative rule for a natural log is much easier than the derivative rule for a common log or a log of some other base. So when you see use logarithmic differentiation to solve a problem, make sure you keep in mind you're doing the natural log of that. So the first thing, notice we've got a pretty nasty thing over on the right. What we'll do is we'll take the natural log of both sides. So we'll have natural log of y equals the natural log of the whole other mess. X to the 3/4 times square root of x squared plus 1 all over 3x plus 2 to the 5th. The reason for doing this is because on the right-hand side, we can use our log laws to separate this now. Remember, when there's multiplication going on, you can separate into separate logs with addition, and when there's division, you can separate it into subtraction. So this will now become natural log of y equals natural log of x to the 3/4 plus natural log. I'm going to rewrite square root of x squared plus 1 as x squared plus 1 to the 1/2, okay, which is the equivalent. And then minus, because you're dividing, natural log of 3x plus 2 all raised to the 5th. The next log law we'll use is that if you have an exponent, you can bring it out front. So we'll have natural log of y equals 3/4 natural log of x plus 1/2 natural log of x squared plus 1 minus 5 times natural log of 3x plus 2. Now we'll just do our derivatives. Derivative of natural log of y will be 1 over y times a y prime, because there's a derivative of a y. Then we'll have 3/4 times our derivative of natural log of x, which is 1 over x, plus 1/2 times our derivative of natural log of x squared plus 1. Well, it's the derivative of the inside over the inside. So we'll have 2x over x squared plus 1. Then we'll have minus 5 times derivative of the inside will be 3 over 3x plus 2. And now we'll neaten up a little bit. 1 over y times y prime will equal 3 over 4x plus, notice a 2 will cancel out of each of these, so we'll have x over x squared plus 1 minus, the 5 will multiply at the numerator, so we'll have minus 15 over 3x plus 2. And we have 2 more steps to go. We now want to get y prime by itself. So we can get rid of the 1 over y by multiplying both sides by y. So we'll get y prime equals y times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And then your last step, one that many people often forget to do, is we are going to replace y with what we knew y was equal to. In the original problem, they told us it was x to the 3/4 square root of x squared plus 1 all over 3x plus 2 to the 5th. So we'll get y prime equals, replace the y with what it was originally, x to the 3/4 square root of x squared plus 1 all over 3x plus 2 raised to the 5th times everything else, the 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And that's your final answer. These are always going to look really messy, but by doing it with logarithmic differentiation, it makes our life a lot easier. So just to summarize the steps we did, we started out, we took the natural log of both sides. and used log laws to simplify the right side of the equation. We then used implicit differentiation to take the derivative of both sides with respect to x. We solved for y prime, so in other words, got y prime by itself by multiplying both sides by y. And then the step that people often forget at the end is replace y with what it was equal to in the original problem. Now, sometimes it might say, find the derivative using logarithmic differentiation, and that should click in your head, I'm using a natural log. Other times, you might have to just recognize that it needs to be used. So let's just talk about the different cases and what you should use. It's important to distinguish between a variable raised to a number, which would be power rule, and a number raised to a variable, which would be an exponential, and we'd have to use our exponential differentiation rule. So here's the 4 different cases we could have. If you have a number raised to a number, like 2 to the third, well, 2 to the third is just 8. That's a constant. That's easy. Derivative of a constant is 0. If you have something with variables raised to a number, well, that's just power rule. Bring the exponent out front. Exponent goes down 1. If you need to do chain rule, multiply by derivative of the inside. If you have a number raised to something with x's in it, that's number 3 there. That is an exponential, so you'll do whatever that exponential is times the natural log of your base, and then if it's chain rule, you do times derivative of the inside. And then the new one, if you have functions in both the base and the exponent, then you must use logarithmic differentiation. And that's something you might just have to recognize. It might not be told to you in the problem. Here's an example of a case of that. We have variables in our base. We have variables in our numerator, or sorry, not our numerator, in our exponent. So we have to know to use logarithmic differentiation. So first step, take the natural log of both sides. Second step, use log laws to simplify the right side as much as possible. Exponent would come out front. Now take the derivative. We'll have 1 over y times y prime on the left side. On the right side, we've got to use the product rule. Keep in mind, x square root of x is really x to the 1/2. So we'll do derivative of the first part. We'll get 1/2 x to the minus 1/2 times regular plus, because it's product rule, regular times derivative. Derivative of natural log is 1 over x. Usually you'll neaten up the right-hand side a little bit. It's not absolutely necessary, but usually makes life a little bit easier. This first part will end up as natural log of x in the numerator over 2 square root of x in the denominator. And then we'll have plus square root of x over x for the second one. Now I would say just leave this as is. Multiply both sides by y, so we'll get y prime equals y times natural log of x over 2 square root of x plus square root of x over x. Now if you wanted that second part in the parentheses, you could write as 1 over square root of x, and then you could even get a common denominator if you felt like it. Last step, replace y with what it was equal to. Y was just x raised to the square root of x, and then we've got all the rest of our stuff. And this would be our derivative, which we got using logarithmic differentiation. One last example for this video. Sine x raised to the sine x. You've got a function of x in the base, a function of x in the exponent. That needs to click in your head that you'll use logarithmic differentiation. Remember, logarithmic differentiation, we're really using natural log. So I have natural log of y equals natural log of sine x raised to the sine x. We'll use our log laws on the right, and we'll have sine x times natural log of sine x. Take the derivative of each side. We'll have 1 over y times y prime equals product rule on the right-hand side. Derivative of the first is cos x times regular of the second, plus, because it's product rule, regular of the first times derivative of the second, which would be derivative of the inside, cos x, over the inside, sine x. We'll neaten up a little. This is 1 over y times y prime would equal cos x times natural log of sine x. Second part, the sine x's cancel out, so you just have cos x. And we'll multiply both sides by y to get y prime by itself. And the part you don't want to forget at the end, replace y with what it was equal to in the beginning. So we have sine x raised to the sine x, and then our whole part in parentheses. And that is our derivative, which we again found by using logarithmic differentiation. That's all for today's video. We'll see you next class period.